If we were together in person, we would start Chapter 6 by working on an interactive circuit construction, but because we're not, I'm going to show you how to do this by simulation. So I've linked a simulation in your course Moodle page, and you can follow along by clicking on the link there. When you click on the link to that simulation, you'll get two options, Intro or Lab. I'm going to click on Intro. Now we're going to start to construct a circuit that illuminates a light bulb. So I'm going to drag a light bulb over into this circuit, and I'm going to power that light bulb with a battery. I need to connect the battery to the light bulb, so I'll use a wire, connect the wire to the battery, then drag and connect the wire to the light bulb. I can disconnect by clicking on a joint and disconnecting, and reconnect just by dragging and snapping things back together. Now, I want to connect my wire to the other end of this battery. So I'm going to drag and click a few of these things together so that I can make a nice square circuit. And voila, we illuminate our light bulb. So why is it that the light bulb illuminates when we connect this circuit together? What would happen, say, if we removed this battery altogether and just connected wires to each other? Why doesn't the light bulb illuminate? What would happen if we disconnected a wire, replaced with a battery, but didn't connect the battery all the way? Why doesn't the light bulb illuminate? The answer is that the key to the illumination of this light bulb is the flow of electrons. In the second half of this semester, we're going to consider matter and the components that make up matter. Even the ancient Greeks knew something about matter. They knew that when they, say, rubbed amber with a cloth or wool, that they could induce a static shock on other things, like, say, frogs that they'd make jump around at lavish parties. And the Greek word for amber derives the word electron. The charges that electrons carry generate electricity. There are a few key terms that we have to think about in order to consider electricity and electrical currents. The first of these key terms is electrical charge. We're going to give electrical charge the symbol lowercase q. Electrical charge is a property innate to matter that allows it to experience a fundamental physical force when exposed to an electrical field. Electricity is a force, sort of like gravity is a force. In order for electricity to work, opposite charges have to interact. An electrical charge is a measure of a physical property related to the electromagnetic force. We measure electrical charge using units called coulombs. So electrical charge is measured in coulombs. Coulombs, abbreviated capital C, gives us a measure of the amount of charge transported in 1 second by a current of 1 ampere. When two or more charges interact with each other, they experience a force. The electromagnetic force is the second fundamental physical force in the universe. Earlier in the semester, we talked about gravitational force as one fundamental force of the universe, and said that electricity and magnetism were an example of a second. Now we're going to discuss that second force. The electromagnetic force, a fundamental physical force of the universe, has a value that's given by an equation very similar to the one that we saw for gravity earlier in the semester. In this equation, the force due to electromagnetism is given by a constant, K. This is Coulomb's constant. Multiplied by the charge on one element and the charge on a second element divided by the distance between those two charges, squared. In this equation, Coulomb's constant, K, is a fundamental physical constant with a value of 9.00 times 10 to the 9th newtons times meter squared per Coulomb squared. Q1 and Q2 are charges of two different substances given in coulombs. D is distance, again, and given in meters. That whole quantity gets squared. This electromagnetic force is attractive if Q1 and Q2 have opposite signs, and the force is therefore negative. This force is repulsive if Q2 and Q1 have the same sign, and the force is therefore positive. So, if Q1 and Q2 are both positive or both negative values, we say that the force between those charges is repulsive. Those two charges repel each other. And, alternatively, if Q1 and Q2 have opposite signs, one positive and the other negative, then the force between them is attractive, meaning that those two charges will attract each other. Opposite charges attract and like charges repel. So let's look at an example of how to use this equation. We're going to calculate the force of attraction between a proton, which has a charge, Q, of positive 1.6 times 10 to the minus 19 coulombs, and an electron, which has an oppositely signed but equal magnitude charge of negative 1.6 times 10 to the minus 19 coulombs, that are separated by a distance of 1 times 10 to the negative 10 meters in an atom. We need Q1 and Q2. We've got one Q, another Q. We need a distance. We've got that here. And we need our Coulomb constant, K, which is given above. To calculate the force of attraction between this proton and neutron, we multiply 9 times 10 to the 9 newtons times meter squared per Coulomb squared times Q1, that was positive 1.6 times 10 to the minus 19 coulombs, times Q2, negative 1.6 times 10 to the minus 19 coulombs, all divided by distance squared. That's 1.0 times 10 to the minus 10 meters, quantity squared. Notice that our units of coulombs will cancel out. Coulombs times coulombs are coulomb squared. Our units of meters will cancel out. Meters squared divided by meters squared go away. Be careful as you're multiplying this through, plugging into your calculator. Make sure that your denominator is in parentheses before you square it. But what we should end up with is a force in newtons of about 2.30 times 10 to the negative 8 power. 2.3 times 10 to the minus 8 newtons. Notice that this is a much smaller quantity than some of the quantities we dealt with in the beginning of the semester. 2.3 times 10 to the minus 8 newtons, 23 nanonewtons. At this point, I'm sure you're thinking, gee, if we can calculate a force between charges, can we also do some of the other cool stuff that we did back at the beginning of the semester? Like think about energies. And sure enough, you're in luck because we absolutely can. We can think about electrical potential energy and electrical kinetic energy analogs. And we might call them by slightly different terms in this chapter, but they'll have the same underlying fundamental principles associated with them. Firstly, electrical potential energy. Because two oppositely charged particles are attracted to each other, it takes energy to overcome that force of attraction and pull particles away from each other. Just like it takes energy in order to lift something up off the ground and counteract the force of gravity. When we pull particles apart from each other that have opposite charges, or when we try to push together two particles that have like charges, those particles want to snap back to where they were. Therefore, they have potential energy due to their charge. That potential energy we call voltage in terminology of electricity. Voltage is the potential energy, PE, that charges have when they are separated from each other. Like lifting a book off of a table and counteracting gravity, separating charges from each other imparts potential energy. We call that potential energy voltage, and we measure it with the unit volts, or capital V for a symbol. A volt effectively tells us how much energy each charge carries, how much energy it's going to take to separate one charge all alone from another. We can express that as a ratio. A volt is equal to the energy per charge. Or V is equal to E over Q. Thus, the potential energy for electricity, volts, is the same as a joule per coulomb. Capital J, joules. Capital C, coulomb, our unit of electrical charge. Batteries are rated on voltage. In this example, we're going to think about how many volts a battery holds. If it uses 7.5 joules worth of energy to transport a 5 coulomb charge across its terminals. So, if we know something about an energy requirement and a charge that's associated, we can calculate a voltage. Here, the energy is 7.5 joules, and the charge, coulombs. 7.5 divided by 5 is 1.5 volts. Most batteries that you have used are likely to be 1.5 volt batteries. All AA, AAA batteries are 1.5 volt batteries. In fact, in the demonstration that we'll do to simulate an electrical current in a circuit, we'll use a Mach 1.5 volt battery to accomplish illuminating a lamp. When we discussed kinetic energy from the perspective of motion, kinetic energy was expended energy, energy of something that's moving. In an analogous way, electrical kinetic energy is associated with motion. And we refer to the motion of electrical kinetics through the term current. Much like a river running generates a current, electricity running generates a current. Like a river's flow, the flow of electric charge is analogous to the kinetic energy in an electrical circuit. Current is a flow of charge over time. The unit for current is one of the fundamental 7 SI units. It is the ampere, or amp for short, abbreviated capital A. The ampere comes from measuring charge over time. Current is equal to charge flowing divided by time. We will give the abbreviation I for current, since we've already used C as an abbreviation for the Coulomb measure of charge. I is equal to Q over T. Here, Q is our charge, measured in coulombs. T is time, measured in seconds. Current, amps or amperes, are equivalent to coulombs per second. In this terminology, since current is a measure of change in charge over time, a wire carrying a current of 4 amps will have a rate of charge flow of 4 coulombs every 1 second. So at this point, let's return to the circuit that we made at the very beginning of this discussion. We are illuminating a light bulb using a battery shown right there. What I want to do here is think about how current is flowing and what the voltage in this system is. So I'm going to go into the upper right-hand corner of this interactive and click on a conventional arrow. And now what we can see is that arrows are generated and they're moving in this diagram. They're moving fairly slowly, suggesting that there's a small amount of kinetic energy in this circuit. We can do 2 things. We can measure the amount of potential energy or voltage in this circuit, and we can measure the amount of kinetic energy or current in this circuit. To measure potential energy, we use a voltmeter, this thing. We'd connect one lead to, say, one side of a battery, and the other lead to the opposite end. And we read the voltage across this battery as 1.5 volts. This is like a typical AA or AAA battery. If I measured the voltage at another location somewhere else along this circuit, I see that the voltage displays 0. When I put one lead on one end of a battery and another lead somewhere off in some distant space, I don't read a voltage at all. In order to read a voltage, we need to be reading across some sort of device. And what's more is a voltage is only read between the location where two leads are placed. So I don't read any voltage difference across this wire length along the bottom. But I do read a voltage difference across the leads or terminals of a battery. A battery works through a chemical reaction that generates an electrical potential or voltage. Even if I disconnect a wire from the battery itself still has a voltage difference from one terminal to the next of 1.5 volts. But current can only flow when one side of the battery is connected to the other. Charged particles can only move from one side of the battery to another. Suppose that I wanted to measure the current in this system. I'm going to use an ammeter to measure current. I'm going to place my ammeter in this circuit somewhere that is capable of measuring current to intercept some of that current and record its value. I see that in this portion of the circuit, we read 0.15 amps. Along our battery, we read 0.15 amps. It really doesn't matter where I place this ammeter. I'm reading the same current all the way through. But should I disconnect any portion of this circuit, my current goes to nothing because there is no longer any flow of electricity. Even though there's still potential energy stored in the battery, that potential energy cannot be transformed into current because there is nowhere for that potential energy to go. I need to be able to connect one end of a battery to another in order to induce current flow. One last thing that I'd like to point out is that our light bulb can have a voltage reading across itself. Here, that voltage reading is 1.5 volts. So I mention that because the next thing that I want to do is add another light bulb, a second one, somewhere in this circuit. Perhaps I will break this wire right here and add in one more light bulb. Now I get current flowing through a whole system illuminating two light bulbs. But notice one thing in particular about two light bulbs here. They are much dimmer. In other words, we don't see as large yellow lines emanating from each one as we did when we just had one light bulb alone. Let's go back. There's one light bulb alone. Look at the yellow lines. Add a second light bulb in. And now we get much smaller, fainter yellow lines. Two light bulbs connected in the same circuit give a much dimmer glow. If I measure the current in this circuit, I measure a lower value, 0.07 amps, compared to the 0.15 we saw before. It doesn't matter where I measure that current, I'm still at that lower value. If I measure the voltage across this battery, I'm still recording 1.5 volts. But if I measure the voltage across a light bulb, now I'm measuring 0.75 volts for the light bulb up at top and 0.75 volts for the light bulb down below. It's almost like that potential energy has been split between the two light bulbs in order to illuminate both of them at the same time. We call this type of circuit a series circuit because these two light bulbs are connected one after the other in series. A series circuit is one in which electrical connections occur successively. In other words, one right after another. One light bulb in line with a second bulb. We can draw a diagram for what that schematic electrical circuit looks like using lines and depictions that are shorthand for things like a battery, and a light bulb, and our wires. In a series circuit, having more than one light bulb resulted in a dimmer overall result than having just one light bulb alone. In a series circuit where we only had one light bulb, that single light bulb illuminated much more brightly. Adding light bulbs in series reduces brightness and it reduces the current flowing through the entire system. So, adding more electrical components in series reduces the brightness and the current. As a result of current decreasing, the brightness of our light bulbs decreases by adding more components in a series circuit. So what is the relationship between the number of components that we've added to a circuit and the voltage, potential energy, and current, the kinetic energy analogs for electrical circuits? Well, remember that in the circuit that we looked at first, where we just had one light bulb, we saw that the voltage was 1.5 volts. And the current moving through this circuit was only 0.15 amps. Is there any way to mathematically relate voltage and current and explain why adding more light bulbs decreases both? Well, it turns out that there is, and an intuitive way to think about this is to think about a river flowing. Instead of charged particles flowing through each one of these circuits, think about a river's flow. And think about jamming a river by adding debris to it, like logs or fallen trees. The more and more stuff you put in the way of a river's flow, the less and less quickly it's going to move, the less kinetic energy of motion it has. So the more barriers we place to our current flow in an electrical circuit, for the same reason, the harder a time our electrical current is going to have at flowing in the first place. This idea has a special name, and we refer to that barrier or resistance to flow. Resistance in electrical circuits is a barrier to electrical flow. All real materials provide some resistance or barrier to an electrical current's flow. This idea of resistance is the key portion that it takes to tie together the concepts of voltage and current in electrical circuits. Resistance which will give the symbol R for, has units of ohms, OHMS. We're going to use the Greek letter omega to symbolize ohms. Omega looks like a horseshoe. The relationship between resistance, voltage, and current is given through Ohm's law. Ohm's law is perhaps the most important equation that we'll learn here and has the most practical utility for you, not only as future educators, but also in being handy people around your house. Ohm's law relates voltage to current and resistance. V equals IR. In Ohm's law, V again is voltage, I is current, and R is resistance to current flow. So that voltage in a circuit is equal to the current times the resistance in that circuit. The more things that resist current flow for a given voltage, the lower our current must be in order to maintain that voltage. In other words, as this gets high, R gets large. Current, I, gets small, and vice versa. I mentioned a second ago that resistance is imbued by all normal materials. So everything in an electrical circuit, every single component, including the wires themselves that hook our electrical circuit up, offer some resistance. Resistance itself depends on 4 key quantities. For one thing, the type of material that we're interested in is key in determining resistance of electrical flow for that material. Metal is much less resistant to electrical flow than, say, glass. A second key characteristic of materials that dictates their resistance or resistivity is the length of a material. The longer a material is, the more space that an electrical current has to travel through, the more likely that electrical current is going to be to encounter some resistance to its flow. So what we'll say is that short wires have less resistance. As length increases, as length goes up, resistance increases. Resistance goes up. There's more opportunity for an electrical current to encounter some resistance. Thirdly, the diameter of a material, or say wire that we're using to connect an electrical circuit, impacts resistance. A very narrow wire has high resistance because it limits the path that individual charges can take. So, large diameters allow charges to spread out and not bump into things as often. As diameters decrease, as they get smaller and smaller, narrower and narrower, as diameters decrease, resistance goes up. And lastly, temperature plays a major role in determining resistance. At high temperatures, things on a very microscopic scale are moving very quickly. We discussed that when we discussed heat and temperature. Microscopic motion is greatest at the highest temperatures. So as temperatures increase, as T goes up, microscopic motion is maximized. And we know that with increasing temperature, motion on a microscopic scale increases. What this means for an electrical current is that there is a higher likelihood and higher frequency with which electrical charges will bounce into or collide with moving particles. A greater opportunity for barrier to electrical current flowing, because it's more likely that some particle is going to fall into a current's path. As temperature goes up, resistance goes up. As an aside to this, we can say that at very low temperatures, resistance is likewise very low. And for some materials, we can generate almost zero resistance if the temperature is small enough. So at very low temperature, some materials exhibit no resistance at all, or effectively 0 ohms of resistance, almost zero resistance. That means that charges can move freely in these materials. We call these materials superconductors. They're capable of conducting electrical current without the inhibition of resistance. So let's use Ohm's law to think about our circuit with just one light bulb in it. A single light bulb in a 1.5 volt circuit, we saw drew a current of 0.15 amps. Let's calculate the resistance of that light bulb. How much was it resisting the flow of electricity in the circuit that we drew in the previous slide? So we've got a voltage, we've got a current, and we'd like to find R. Using Ohm's law, V equals IR, we can rearrange and solve for R. R is equal to voltage over current. Our voltage is 1.5 volts. Our current is 0.15 amps. 1.5 divided by 0.15 is 10. 10 ohms, where the unit for resistance is the Greek letter omega, ohms. So back one more time to the circuit that we compiled a few slides ago. We'd measured the voltage across our light bulb as 1.5 volts. We measured the current in this system as 0.15 amps. And we calculated using Ohm's law that the resistance that this light bulb provides to the electrical circuit is 10 ohms. If I click on this light bulb, sure enough, the resistance located down here at the bottom is 10 ohms. If I increase the resistance that that light bulb imparts, we can see that our current goes down as resistance goes up in order to maintain the same voltage. At the highest resistances, our current slows to a crawl. As we decrease resistance, our current increases. And at near zero resistance, we have freely moving electrons, basically an infinite current. If we place a second light bulb in series in this circuit, then what we see is that the current drops even more because we've placed more resistance in this circuit, but so too has the voltage changed across light bulbs. We see that the voltage is 0.75 across each light bulb, rather than the 1.5 it were before. It's almost like our voltage got cut in half. So, why is that? In order to understand this, we need to talk about one final key term, and that is electrical power. We discussed power when we talked about motion. This was amount of energy expended per amount of time. In an electrical circuit, power takes on a similar meaning, except now instead of describing it with joules per second, we're going to describe it with our analogs of electricity's energy, voltage, and current. If you're into mathematics, we can do this mathematically. We said back in our equations of motion that power was equal to energy divided by time. And in this chapter, we're defining energy in an electrical circuit in terms of voltage and charge. Voltage times charge is the energy associated, the potential energy associated with an electrical circuit. In this relationship, if I take Q over T to be another electrical component that we've defined, this is the same as current. Power in an electrical circuit is given as voltage times current. And power is still measured in watts, our SI unit of power. Capital W for short. V is voltage, and I is current. Power is equal to voltage times current. As an example of how we can apply the concept of power to an electrical circuit, let's look at this problem. An 1100 watt hairdryer is designed to operate on a typical household electrical circuit which has a voltage of 120 volts. How much current does this hairdryer pull? Since we know power and we know voltage, we should be able to get current using our power equation from above. Power is voltage times current. 1100 watts is equal to 120 volts times current. 1100 divided by 120 gives us our current in amps. This particular hairdryer pulls 9.2 amps worth of electrical current in order to operate. So imagine having this hairdryer running and then simultaneously hooking something else up to the same circuit in series that pulls a similar amount of current, and then something else, and something else, and something else. Soon, you might be drawing so much current that you overwhelm your series circuit. Overwhelming a circuit means things get so hot that they burn up or blow out. So most electrical circuits are wired not in series, but instead in parallel. We'll talk about that next. Suppose that I want to set up a circuit to power two light bulbs simultaneously. I could put those two light bulbs one right after another in series, or I could hook them up like this. What I'm about to do is draw a wire that comes out of a battery terminal and connects to either one of these light bulbs. There's one light bulb. Notice the lines on it, how illuminated it is, and the current moving through it. Now I'm going to connect a second light bulb. Notice the lines on it. and how the current moves. If I disconnect the second light bulb, has anything happened appreciably different to the first one? If I reconnect, is there any noticeable difference between these two light bulbs' luminosities? It really doesn't look like it outwardly. Let's measure the voltage across these light bulbs. If I disconnect the bottom one and measure voltage, here I'm using a 9-volt battery rather than a 1.5-volt battery and a 10 ohm light bulb again. And if I measure the current through this system, 0.9 amps, where there's a 9-volt difference across the single light bulb. Well, let's connect the second light bulb. The current has changed. It's gone from 0.9 to 1.8, but the voltage hasn't. In fact, if I measure voltage across this second light bulb, it is also 9 volts. My current's changing, but my voltage across these light bulbs is staying the same. Both light bulbs can still illuminate to the same brightness that any one did all by itself. But now we're able to split this circuit into 2 paths. In one path, our electrical circuit can illuminate this first light bulb. In an alternative path, this electrical circuit can illuminate the second one. Which one's preferable? Both light bulbs exhibit the same resistance to electrical flow. They are both 10 ohm light bulbs. So which one is preferable? Which path do the electrical charges choose to flow? The answer is that they choose both paths, and they do so equivalently, so that both light bulbs stay illuminated to the same degree. This is called a parallel circuit. In a parallel circuit, there are multiple paths or branches through which current might flow. In depicting a diagram for a parallel circuit, we might see something that looks like this. A battery that produces some voltage, but that voltage could go down one of any 2 paths, either to illuminate the first light bulb or the second one that we placed in our circuit. Here, electrons are moving through this path, and they're moving through this path to illuminate 2 light bulbs to the same intensity as any one light bulb all by itself. We get the same intensity in these 2 light bulbs connected in parallel as we got for one light bulb all on its lonesome. In a parallel circuit, we maximize efficiency in being able to connect more than one device. And this is the way that a household's electrical circuit is wired. So that if you say turn on a hairdryer and then turn on a washing machine, you're not going to overwhelm your system and cause both to function abnormally. As an aside to this discussion, I'd like to briefly mention what the difference between a parallel circuit and a short circuit is. In a parallel circuit, multiple devices with resistivity are connected in multiple branches. And we see a voltage through each of them that's not diminished by the presence of more devices. I can take out a device and others still continue to function normally. But what would happen if I connected the 2 wires down below, where the light bulb on the bottom used to be? Well, suddenly I would make a bridge across this circuit that allows electrons to pass through something unimpeded. Remember, this light bulb has resistance in it and resists the flow of electrical current, but wires have far less resistance. And won't resist the flow of electrical current. Suddenly we introduce a way for electrons or charges to move through this circuit bypassing resistance. And now electrons won't move through our light bulb at all. Rather, they're taking the path of least resistance, which completely bypasses the light bulb in the first place, in order to speed their way maniacally through this circuit. We say that the electrons are now taking a shortcut, or are short-circuiting this electrical circuit. A diagram for a short circuit might look like this. Some electrical source, like a battery, is connected to, say, a light bulb down here. But then we go ahead and place a wire between two junction points, bypassing that light bulb. This is a short circuit. It provides a quick and convenient route for electrical charges to move and bypass our light bulb altogether, and will quickly burn out our circuit as a whole. So what we've seen is that electricity has analogs of energy, voltage, and current, which are related to each other through the concept of resistance, and that all materials offer some resistance, so that there's no way to transmit electric energy with 100% efficiency. Therefore, electricity is a commodity that we end up paying for in order to power all of our modern lives. So, what are we actually paying for when we pay for electricity? Are we paying for voltage, or current, or power? Turns out we're actually paying for energy. Energy in the sense of electricity. And the cost of electricity is always given as amount of power supplied times the amount of time that power has been supplied, times the going rate for that energy. Power times time is energy, and electrical companies sell energy at a particular rate of cost. So let's do an example problem. Often utility companies will charge you by the kilowatt hour, kWh. Kilowatt is a unit of power, and hour is a unit of time. Kilowatt hour costs 10 cents in this particular example, and you are going to operate a light bulb continuously for 30 days, an entire calendar month, like the entire month of April. And that light bulb is a 100-watt light bulb. So we know that the amount of power that's being drawn is 100 watts. And the amount of time that it's been drawing that power is 30 days. We need power to be in kilowatts and time to be not in days but in hours, according to these units. Power, kilowatts, time, hours. So let's do two things first. Let's take this power and convert it to kilowatts. To convert watts to kilowatts, we just divide by 1,000. Move our decimal 3 spaces to the left. To get our time in hours instead of days, we can just multiply our number of days by the number of hours in one day. That's about 720 hours. With these quantities, we can come up with a cost to operate this light bulb. The power, 0.1 kilowatts, times the time, 720 hours, times the cost, 10 cents per every 1 kilowatt hour. Our units of kilowatts can go away. Our units of hours can go away, and we'll be left with just a cost unit. 0.1 times 720 times 0.1 is $7.20. It costs $7.20 to operate a single light bulb, a 100-watt light bulb, continuously for an entire month. This is just one aspect of a component of your household's electronics. So imagine that this builds up pretty rapidly with more devices that are being operated. For the laboratory component of this chapter, you've got several exercises in PowerPoint slides outlined for you on your course Moodle page. I would like you to use the simulation tool that we've discussed here in this lecture to recreate virtual electrical circuits using the components that you have available to you in the simulating tool. After you've done that, I will post some questions for you to follow up.